Hi, what's up people? Mr. Highway here. Today I received a text from a student who asked me about binary numbers. Well, I have taught the binary numbers before, so today I'm just going to share with you how this thing works. Okay, it's just going to be a very simple lesson to convert from binary numbers to decimal numbers and back. And we also look at how we can use the calculator to do the operations on this. Alright, so here goes. First, the concept. So we look at binary numbers and decimal numbers in terms of its place values. So for decimal numbers, which is what we're very familiar with, if you look at the value 0, of course it is 0, right? Now, if it's 1, then we put 1. We have a special symbol for 1. And then 2 is 2, 3 is 3, 4 is 4, 5, 6, 7, 8, 9. But when we come to 9, we realize that we have no more symbols to represent a 10 after that, okay? So we say that, well, why don't we write 1, 0? So this 0 here is actually, remember, if you learn this in primary school, you say that the first digit represents the ones, right? And the second digit represents the tens. 1, 0, well, 1 is lesser than 9, 0 is lesser than 9, but the 1 in the second place is powerful. A 1 here represents the 10 already. Yeah, so the 1 here represents the 10, and then 0 is 0, okay? So then we go to 11, 1, 10, and 1, 1. That makes sense, right? Okay, so 12 is 1 and 2. And we know that in the decimal, the third digit actually represents hundreds. Okay, so if you have 1, 1, 2, that's 100, 110, and 2 ones, right? Yeah, so 110 and 2. So this represents the hundreds. This represents the thousands. Now, we kind of generalize this and we say that the ones, right, actually will be 10 to the power of 0. The tens is 10 to the power of 1. The hundreds is 10 to the power of 2. And the thousands is 10 to the power of 3. All of them, because decimal is a base 10 number, so we'll see base 10 here. The power will be the first, second, third, fourth place, right? But for first place, you have a power 0. Second place, you have power 1, third 2, and fourth 3. Okay, the power is always 1 less than the place number. So for binary, if we follow the same logic, we will see that the first place will follow 2 to the power of 0. Okay, the second place will follow 2 to the power of 1, because these are now binary, that means base 2 numbers, right? Base 2. And you have 2 to the power of 2, 2 to the power of 3. So if you are writing this in English, then the first would be the ones, the second would be the twos, the third would be 2 squares would be 4, so this would be 4s, and 2 to the power of 3 is 8, so you have 8s. Now, instead of ones, tens, hundreds, and thousands, the digits of a base 2 number will represent 1s, 2s, 4s, and 8s, okay? So at this point, some of you might be very confused, but let's look at some examples and it'll be a lot clearer. Okay, so to represent a 0 is just a 0, yes? Okay, and to represent a 1, it'll be a 1. For binary numbers, we only have 2 types of digits, okay? Only 1s and 0s. So when we come to 2, right, we have run out of symbols to represent it, and we will have, then it's a 1, 2. Can you see 1, 2, and 0, 1? So a 1, 0 in a binary represents 2 in value. So if you go on, a 3 would be a 1, 2, and 1, 1, right? A 2 and a 1 together is 3, right? Yeah? So 4s would be 1, just 1, 4. Can you see that? Just 1, 4. We don't want to have 2s, we don't have the 1s, okay? Now, another example that I use to help students understand this is that, let's say you go to a country, you know, for a tour, and the country only has 4 types of banknotes. The first one is a $1 note, okay? The second type is a $2 note. The third type is a $4 note, and the fourth type is an $8 note. Supposing in this country, when you want to buy stuff, you have to give exact, you can't give change, okay? So if you want to buy something that is, say, $5, okay, so what would you need to give? Of course, you will use a $4 and a $1 to pay for $5, right? And you will not use $8, you will not use $2. So that means this is 1 and 0 and 1. You're not using the 8, so this is 0 as well, which you don't need to put in. Yeah, so you can see that 101 is 5. How about say $10 then? $10, when you look at this, is $8 plus $2, right? So you have one $8, you have one $2, you don't use 4, you don't use 1. And so there you have it. 1010 is $10. If you follow the same logic, 1010 is $10, 5 is 101. Okay, so why don't you give it a try and fill up the rest? Okay, I'm going to leave the answer in the description section. Now I'm going to do a simple example to convert binary numbers to decimal. Remember that our first binary digit represents ones. The second represents twos. Okay, if you can't remember, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. Okay, if you press calculator, you see that this is 1, this is 2, this is 4, and this is 8. So the third digit 4s, and the fourth digit 8s. Let's say we have 101, okay? So 101, that'll be 1, 1, and 1, 4. So 4 plus 1 is 5, okay? So 101 will be equals to 1 times 4. Okay, the 0 we just ignore, plus 1 times 1. And that gives us a 5. Part B, you have 1101, and that's 1101. Okay, and 1 here represents a 1, so this is just a 1. This represents a 2, but then we're not using 2s, so we just ignore. The third digit represents a 4, so you have 4 times 1, which is 4, right? And then the fourth digit represents an 8, so that's 1 times 8 is 8. So 1101 will be equals to 13. Part C, okay, now it's a bit more tricky already because we have so many digits, right? So if we carry on, okay, let's see, there are 7 digits in this number, 1, 2, 3, 4. So the next one will be 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. 1, 2, 3, 4, 5, 6, 7 digits. Okay, so this is 8s, we carry on, we have the 16s, okay, 2 to the power of 4 is 16, 2 to the power of 5 is 32, so this is 32s, and 2 to the power of 6 is 64s. Okay, so if you have 1, 1, 1, 0, 1, 0, 1, okay, the first digit here is a 1, okay, 1s, 2s, and 4s. So this one is actually a 4, you have 1, 4, we add up. 8s, we don't have any 8s, 0, 8s, and then 1, 16, the next one is a 16, and the next one is a 32, and the next one is a 64. So basically we just add them up and we get the value for 1110101, okay, which is 96, 106, 112. 112 plus 5 is 117. So now we're going to convert numbers from decimal to binary, okay, that means base 10 to base 2. So here we have 3 examples. The method we're going to use is called a division ladder because it looks like a ladder and we keep doing division. Let's look at the first one, it's 18. We're going to convert 18 from decimal to binary. So it's like those ladder that we draw for LCM, HCF, right? We just write an L here and then we divide by 2. We divide by 2 because we're going to convert to binary, okay? So if you're going to do other bases, you just divide by whatever number it is. Divide by 2, you're going to have 9, right? Okay, now this is important. You have to write the remainder here. 18 divided by 2 is 9, remainder 0. We divide by 2 again and you get 4 remainder 1, right? 4 remainder 1. And you divide by 2, this is 2 remainder 0. Divided by 2 again, you get 1 remainder 0. Okay? So watch this, 18, but then 18 in decimal. Okay, I'm going to write a subscript of 10 here, a little number that is slightly lower, to indicate that this is base 10. And I'm converting it to binary, which is a base 2 number, and the result is this. Okay, 1, 0, 0, 1, 0, this way up. Okay, so the result is 1, 0, 0, 1, 0, base 2. Part B, let's look at 69. We're going to convert it from decimal to binary. We divide it by 2, and that's 34, remainder 1, right? 34 divided by 2, again, we just keep dividing by 2. We have 17, and the remainder is 0. Divided by 2, we get 8, and remainder 1, right? So every time the odd number divides by 2, you get the remainder 1. Divide by 2, you get 4, remainder 0. Divided by 2, you get 2, remainder 0. And 2 again, you get 1, remainder 0. So 69 is then equals to 1, and then 3 zeros, and then 1, 0, 1. 69 base 10 is equals to 1, 0, 0, 0, 1, 0, 1. Part C, we have 105 here. Okay, so same thing, we divide by 2, you get 52, but remainder 1. Divide by 2, we get 26, remainder 0. Divide by 2, you get 13, remainder 0. Divide by 2, you get 6, remainder 1. Okay, 2 again, we get 3, remainder 0. And divided by 2 again, we get 1, remainder 1. Okay, so this is the important step here that sometimes I also miss. And it is that the last one, you get two numbers. Okay, so the quotient and the remainder. Okay, these two have to come. So you get 1 remainder 1, and you have the rest here. Okay, this way up from bottom up. And so we say that 105 base 10 is equals to 110, 1001 base 2. So now we're going to convert each of these numbers from decimals to binary using the calculator. The numbers are exactly the same as what we did earlier on. So we're just going to use the calculator to check if the result is correct. So, okay, mode, base n, and we'll see decimal. Okay, now these numbers are in decimal, so I'm just going to straight away press 18 here, equals, then I press binary, and we have 10010. Part B, 69. So I go back to decimal, press 69, equals, and I press binary, we get 1000101. Part C, decimal again, 105. Binary, okay, remember to press equal, okay? You have to press equal before you go to binary. So you got 1101001. Okay, so let's do a check. So first we have 10010. That's correct. 1000101. 1000101. Okay, correct. 105 is 1101001. 1101001. Okay, good. So that's it for today's lesson on binary numbers. If there's anything else you would like me to share, please leave in the comments. Like and subscribe to this video if you find it useful, and I'll see you in the next video. Bye!